Imagine boarding an airplane that weighs hundreds of thousands of kilograms. Inside are hundreds of passengers, thousands of liters of fuel, rows of seats, engines, and tons of metal. Then the plane accelerates down a runway, leaves the ground, and climbs several kilometers into the sky. And somehow it stays there for hours. But here's the strange part. Gravity never stops pulling the airplane downward. The airplane doesn't become weightless. It doesn't turn off gravity. So how can something this massive stay in the air at all? The answer is hidden in four forces constantly fighting against each other: gravity, lift, thrust, and drag. And once you understand how those forces work together, you can finally understand how a machine weighing hundreds of tons can fly through the sky. At any moment, an airplane is being affected by four major forces. The first is weight. Gravity is constantly pulling the airplane toward the ground. It doesn't matter whether the plane is flying at 10,000 meters or sitting on the runway. Gravity is always there. The second force is lift. Lift acts in the opposite direction, pushing the airplane upward. When lift is greater than the airplane's weight, the plane climbs. When the two forces are balanced, the plane can maintain its altitude. The third force is thrust. Thrust pushes the airplane forward. This is created by the engines. And the fourth force is drag. Drag is air resistance. It acts against the airplane's motion, trying to slow it down. So, in the simplest possible way, flight is a constant battle. Weight pulls down. Lift pushes up. Drag pulls backward. Thrust pushes forward. When the forces are balanced, the airplane can cruise smoothly through the sky. But if the airplane is going to fly, one force is especially important: lift. Because without lift, no matter how powerful the engines are, the airplane is going straight back to the ground. So what exactly creates this upward force? The answer begins with the airplane's wings. A wing might look like a simple curved piece of metal, but its real job is much more interesting. As an airplane moves forward, its wings move through the air. And although air looks empty, it is made of molecules. Those molecules have mass, and they can be pushed, redirected, and accelerated. The wing takes advantage of that. As the wing moves forward, its shape and angle force a large amount of air downward. And according to one of the most fundamental laws of physics, when the wing pushes air downward, the air pushes back upward on the wing. That upward reaction is a major part of what creates lift. You can actually feel a similar effect yourself. If you stick your hand out of a moving car window and tilt it slightly, the air pushes your hand upward. The faster the car moves, the stronger that force becomes. An airplane wing is doing something similar, but on a much larger scale and with a carefully designed shape. The wing is constantly moving through the air, redirecting an enormous amount of it downward. The air pushes back, and that upward force helps support the weight of the entire airplane. But there's more to the story than simply saying the wing pushes air down. The shape of the wing also changes how air moves around it. And this creates differences in pressure that contribute to lift. To understand why, we need to look more closely at what happens to the air as it flows over and under the wing. Imagine looking at the cross-section of an airplane wing. The top is usually curved, while the bottom is often flatter. As the wing moves through the air flowing around it is forced to change direction. Some of the air travels over the top of the wing. Some travels underneath. The shape and angle of the wing create different conditions in these two flows. The pressure around the wing changes, and the result is a net force pushing upward. But here's something important. The popular explanation that air traveling over the top of the wing has to meet the air underneath at the same time is an oversimplification. The air doesn't have to arrive at the trailing edge simultaneously. In reality, the wing changes the flow of air around it, creating a complex combination of pressure differences and downward moving air. The key idea is that the wing interacts with a huge volume of air. It redirects that air downward, and the pressure forces acting across the surface of the wing produce an upward force. Both effects are connected. The air moving around the wing creates a pressure distribution. That pressure distribution causes the wing to push air downward. And the reaction to that change in the air is lift. This is why the shape of the wing matters so much. But the wing's shape isn't the only thing that matters. The angle at which the wing meets the incoming air is also extremely important. This angle is called the angle of attack. If the angle is too small, the wing may not create enough lift. If the angle is increased, the wing can redirect more air downward and produce more lift. But if the angle becomes too large, something unexpected happens. The smooth flow of air over the wing can break down. The wing can lose a large amount of lift. This is called a stall. And despite what the name sounds like, a stall doesn't mean the engine has stopped. It means the wing is no longer producing enough lift to maintain normal flight. So an airplane doesn't simply fly because its wings are curved. It flies because the wings are carefully designed to control the flow of air around them and because the airplane is moving through that air at the right speed and angle. Now imagine the airplane flying through the air at hundreds of kilometers per hour. Every second, its wings are interacting with an enormous amount of air. That air is being pushed, redirected, and accelerated downward. And the faster the airplane moves, the more air the wings can interact with in a given amount of time. This is one reason speed is so important to flight. If an airplane moves too slowly, its wings may not be able to generate enough lift to support its weight. But speed alone isn't enough. The wing also needs the right angle. Imagine holding your hand out of a moving car window. If your hand is perfectly flat and aligned with the airflow, the air may mostly move around it. But tilt your hand slightly and the air begins pushing it upward. Tilt it too much and the airflow can become chaotic. An airplane wing works with the same basic idea, but with a much more carefully engineered shape. The pilot doesn't constantly point the entire airplane upward to keep it in the sky. Instead, the wing is designed so that as the airplane moves forward, it creates the right pattern of airflow around itself. And the airplane's control systems constantly make small adjustments to maintain that airflow. This is also why an airplane can continue to glide even if its engines stop producing thrust. The engines are essential for keeping the airplane moving forward over long periods of time. But the wings can still create lift as long as the airplane is moving through the air. The airplane will gradually lose altitude as it converts its height into forward motion. But it doesn't simply drop straight out of the sky. The wings continue interacting with the air. And this reveals something important about flight. An airplane isn't floating in the sky. It is constantly moving through the atmosphere, using that movement to create lift. But movement requires energy. And that's where the engines come in. Because the wings can create lift, but something has to keep pushing the airplane forward. The engines are what provide that forward push. On a modern jet airplane, the engine begins by pulling in enormous amounts of air through the front. Inside the engine, powerful rotating blades compress the air, squeezing it into a much smaller space. Then fuel is injected and ignited. The resulting gases become extremely hot and expand rapidly. But they have nowhere to go except toward the back of the engine. So the engine accelerates a huge mass of air backward at tremendous speed. And according to Newton's third law, every action has an equal and opposite reaction. The engine pushes air backward. The airplane is pushed forward. That forward force is thrust. You can imagine standing on a skateboard and throwing a heavy object backward. As the object moves backward, you move forward. A jet engine does something similar, except instead of throwing one object, it continuously accelerates enormous amounts of air backward. And it does this thousands of times every minute. The important thing is that thrust doesn't directly lift the airplane into the sky. Its main job is to keep the airplane moving forward. The wings then use that forward movement to create lift. This is why the four forces of flight are connected. The engines create thrust. Thrust moves the airplane forward. The forward motion allows the wings to interact with the air. The wings create lift. And lift opposes the force of gravity. At the same time, the air creates drag, trying to slow the airplane down. So the engines have to produce enough thrust to overcome that drag and keep the airplane moving at the required speed. A flying airplane is therefore not just an engine pushing a machine through the sky. It is an entire system working together. The engines create forward motion. The wings convert that motion into lift. And the airplane has to constantly control both forces to remain stable. But an airplane doesn't just fly straight ahead. It has to climb, descend, turn, and change direction. And to do that, the wings and tail have a series of specialized movable surfaces. The most obvious control surfaces are found on the wings and tail. At the back edge of each wing are small movable surfaces called ailerons. When one aileron moves up and the other moves down, the wings produce different amounts of lift. One side rises, the other side falls. The airplane rolls to the left or right. This is how the airplane banks into a turn. At the rear of the airplane is another important surface called the elevator. The elevator controls the airplane's pitch. When the pilot moves the elevator, the nose of the airplane can move upward or downward. Point the nose higher, and the airplane can climb. Point it lower, and the airplane can descend. Then there's the rudder, mounted on the vertical tail. The rudder controls yaw the movement of the nose from side to side. Together, these control surfaces allow the airplane to move in 3 dimensions. It can roll, it can pitch, and it can yaw. But the pilot isn't manually fighting every gust of wind and every tiny change in airflow. Modern airplanes use complex control systems and computers to help make constant adjustments. Sensors monitor the airplane's speed, altitude, orientation, and movement. The control systems then adjust the aircraft to keep it stable and on course. In some modern aircraft, the pilot's controls don't directly move the control surfaces through a series of mechanical cables. Instead, the pilot's input is interpreted by computers, which then send signals to the aircraft's control systems. This allows the airplane to make incredibly precise adjustments. And these adjustments are happening constantly. Even when the airplane appears to be flying perfectly straight, the air around it is never perfectly still. The airplane is continuously responding to small changes. But before an airplane can cruise smoothly through the sky, it first has to overcome its own weight. And that happens during one of the most dramatic parts of any flight: takeoff. When an airplane is sitting on the runway, its wings are already capable of creating lift. But there isn't enough airflow over them yet. The airplane needs to start moving. As the engines produce more and more thrust, the airplane accelerates down the runway. The wings begin moving faster through the air. And as the speed increases, the amount of lift the wings can generate also increases. At first, the airplane is still firmly on the ground. Its weight is being supported by the landing gear. But the faster it moves, the more the wings push air downward and the stronger the upward force becomes. Eventually, the airplane reaches a carefully calculated speed. At this point, the wings are producing enough lift to support the airplane's weight. The pilot gently raises the nose. This changes the angle at which the wings meet the incoming air. The angle of attack increases, and the wings generate even more lift. When the upward force becomes strong enough, the airplane rises from the runway. The important thing is that the airplane hasn't suddenly become lighter. Gravity is still pulling it downward with exactly the same force. The difference is that the wings are now generating enough upward force to oppose gravity. The landing gear leaves the ground. The airplane continues accelerating, and the aircraft begins climbing into the sky. As it climbs, the pilot and the airplane systems constantly adjust the aircraft's speed, angle, and engine power. Every part of the flight is a balance. Too little speed can reduce lift. Too much angle can disturb the airflow. Too little thrust can allow drag to slow the airplane down. But when the forces are properly balanced, the airplane can continue climbing until it reaches its cruising altitude. And once it gets there, the airplane doesn't need to keep accelerating forever. It can settle into a stable balance between the 4 forces of flight. Once the airplane reaches cruising altitude, the goal is no longer to climb. It needs to maintain its height. And this is where the 4 forces become balanced. The airplane's weight is pulling downward. Lift is pushing upward. Thrust is pushing forward. And drag is pulling backward. During steady, level flight, lift is approximately equal to weight. And thrust is approximately equal to drag. The airplane continues moving forward at a relatively constant speed and stays at roughly the same altitude. But this doesn't mean absolutely nothing is happening. The air around the airplane is constantly changing. There are gusts of wind, changes in air density, small changes in speed, and turbulence. The airplane's control systems constantly respond to these changes. If the airplane begins to lose altitude, the controls can adjust the aircraft's attitude or engine power. If it begins to climb when it shouldn't, the controls can make the opposite adjustment. If the airplane starts rolling slightly to one side, the control surfaces can correct it. The airplane is constantly making small adjustments to maintain the balance. And this is one of the most important ideas about flight. An airplane does not stay in the sky because it reaches a certain altitude and then simply remains there. It stays in the sky because the forces acting on it continue to balance each other. The wings keep generating lift. The engines keep producing thrusts. The aircraft's shape creates drag. And gravity continues pulling downward. As long as the airplane maintains the necessary conditions for flight, this balance can continue for hours. But what happens when something changes? What if the engines lose power? What if the airflow over the wings becomes disturbed? And what exactly happens when an airplane experiences turbulence or a stall? One of the most misunderstood parts of flying is what happens when something goes wrong. Take engine power, for example. If a jet engine stops producing thrust, the airplane does not suddenly lose its ability to fly. The engines provide forward motion, but the wings are what create lift. As long as the airplane is still moving through the air, the wings can continue generating lift. The airplane will begin to descend, but it can continue gliding. In fact, airplanes are designed with this possibility in mind. The pilots can use the airplane's altitude as stored energy. As the airplane gradually descends, that altitude is converted into forward motion, allowing the wings to continue working. Another phenomenon is turbulence. Turbulence occurs when an airplane flies through air that is moving irregularly. The airplane may suddenly move up, down, or sideways. But the airplane isn't falling out of the sky every time it shakes. The entire aircraft is still flying through the atmosphere, and its wings are still generating lift. The movement is caused by changes in the air around the airplane. Then there's a stall. A stall happens when the wing's angle of attack becomes too large and the smooth airflow over the wing breaks down. The wing temporarily loses a significant amount of lift. But a stall is not the same as an engine failure. And it does not mean the airplane is permanently unable to fly. The aircraft can recover by reducing the angle of attack and restoring proper airflow over the wings. Modern airplanes also have systems designed to help pilots monitor and manage these situations. The point is that flight is not about one single thing keeping the airplane in the sky. It is a system of forces, airflow, engines, wings, and control systems working together. And that brings us back to the question we started with. How can a machine weighing hundreds of tons stay in the air? The answer is not that gravity disappears. It is that the airplane is constantly using the air around it to create the forces it needs to fly.